flap my gums for the next 30 minutes or so. So basically all we're going to do today is talk about experiment 5, some background on chromatography, and then the actual procedural details. All right. Once we finish that talk, you guys need to do a few things to kind of get ready to do experiment 5. Namely, you're going to need to pull spotters. So you probably remember doing this back in 420. You'll need to wash test tubes, because that's what you're going to be collecting your fractions in. And these are not the glass test tubes in your locker. These are, I've got some plastic test tubes. And you'll need to probably wash about 50 of them. And then you need to determine the solvent system that you're going to be running your column in. Okay? And so we'll get into all of this, the specifics of it all in just a second. But I did want to remind you that Monday is a holiday, so don't come. So yeah, President's Day, I think, is that what it? Yeah, it's President's Day. And so you don't have to come to lecture or lab for Monday. So that means our next meeting is going to end up being next Wednesday, a week from today. That's when you will actually start your column. And don't forget, that's when experiment 3 will be due. Okay? Any question about scheduling before we get started? Okay, then why don't we go ahead and get started with the talk. So I wanted to just kind of remind you about some of the fundamentals about chromatography. So when I talk about chromatography, you've already been exposed to at least 2 types of it, right? Last semester, you did thin layer chromatography. That was probably your first experiment. And then you also did an experiment relating to gas chromatography. But all types of chromatography have a couple things in common. Number one, all chromatography refers to a method of separating mixtures. And it does so specifically by passing the mixture through a different media. So for instance, when you were doing thin layer chromatography, you were using these little TLC plates, and so the spots were traveling in the solvent system, and they were traveling through the silica on the silica plate, right? And as such, any type of chromatography is going to always have 2 separate phases. We always have what we call a stationary phase. And this is the phase that the mixture is passed through. And we always have the mobile phase. And the mobile phase is what carries the mixture. It is what carries the mixture through the stationary phase. All right? So, column chromatography is going to follow kind of these same guiding principles. All right, has the same purpose and uses the same types of phases. All right. So why do we even need to worry about column chromatography? Why do we use it? It's kind of a necessary evil in organic chemistry. They are a pain to run, but it's something that you have to learn to do. I can't even tell you how many columns I've run in my life, especially in grad school. I was probably running at least 1 a day for a good 5 years and more. But anyway, it's something you just have to learn to do because you have to do it. So think about running a reaction. If you were running a reaction, it is very rare when you mix your reactants together, you give them some time to react, and then you come back and you isolate one pure product. It's nice when it happens, but it almost never does. Um, what is a lot more common is think about the nitration reactions you did. You ran that reaction, and then I think all of you ended up with more than one thing in your reaction mixture at the end. Some of you had starting material, some of you had ortho product, some of you had ortho and para product, some of you had ortho, para, and then dinitro products. So it is what is most common when you run these reactions is that you end up with multiple things in your reaction mixture at the end. And so in order to take something that you've made and carry it into a second synthetic step, you've got to clean it up. You can't just take this soup of products and carry it into a second synthetic step, right? Because then that 2 or 3 products that you ended up with at the end of reaction 1 ends up becoming 6 to 8 different things at the end of reaction 2. And it's just sloppy. And nobody does it that way. Nobody who's any good does it that way. So what is general practice is you do a reaction, you clean it up, and you isolate the desired compound, and then you take that pure desired compound into the second synthetic step. And then you clean that up and isolate the pure product desired from the second reaction and carry it into the third, etc. You're always starting a reaction with one pure product. Okay? So that's where column chromatography comes in. Now, you've talked about how to purify things already. Last semester, most of you probably did a recrystallization, which is a nice way of purifying solids. But, and they're useful, but they do have some limitations. They're only good for solids, number one, and they're only good if you only have a small amount of impurity. So, column chromatography is going to allow us a lot more versatility when it comes to separation. And it does so because there are 4 variables that we can tweak when running a column. And with these 4 variables, it allows us the ability to separate virtually any mixture you could imagine. All right, so it's a very, very powerful tool for separating mixtures of any kind. All right, and so that's what we're going to spend a little bit of time talking about, kind of the 4 variables, and then I'm going to spend a little bit of time talking to you about the actual procedure, what you're going to come in here next Wednesday and do in order to run your column. And so I'll make a deal with you, and that deal is, if you take really good notes in terms of the procedure today, you don't have to do a pre-lab for this experiment. Okay? What I'm trying to emphasize here is there are a lot of little details that you really have to pay attention to in order to run a successful column. And if you don't, then your column's likely to fail. So if you take really good notes today, you'll have them for next Wednesday when you come in to do your column. And if you pay attention to them, then you'll hopefully have a successful column. But I know it's going to be a week of lag time in between the time we talk about it and then the time you do it. So, you don't want those little details to fall through the cracks as you begin to set up and run the column. Okay? So my suggestion is take really good notes with regards to the procedure today, and then next week when you come in to do it, hopefully everything will work a lot more smoothly. Okay? Okay, so before we get started on the column, I just want to show you kind of a diagram, and so you'll have some idea of what I'm talking about through this process. So your column is going to end up looking something like so there we go. So the column literally is just a glass tube, all right? And in that tube, what I'll try to explain here what the when you're looking at the color coding of it. This blue in the column is the stationary phase. So you pack your column with a stationary phase. Once you've got the column packed, you're going to apply your mixture, and the mixture here is the green band. So you apply your mixture, and then you add the mobile phase on top. Okay? And then whenever you're ready, you'll open up the valve, and the solvent will start traveling through, and the mobile phase will run down the column, carrying the mixture through the stationary phase. And ultimately, what that does, because these different mixture components travel down the column at different rates, as they make their way down the column, they end up separating out from one another. And that's the goal, to separate the mixture. And so what you're going to be doing as you run the column is you're going to be sitting there with test tubes down here, collecting test tube after test tube after test tube after test tube. Okay, these are what we call the fractions. And at some point when you're done with your column, you're going to analyze those fractions. Okay, trying to figure out, well, where is my compound A? Where is my compound B? In what fractions do they reside? Okay? Does anybody have questions about this kind of general picture of the column chromatography? Okay, then I'm going to go ahead and turn this off, and we can start talking about the specifics. So the four variables that we have the ability to change when it comes to column chromatography. The first one is the identity of the stationary phase. All right. So for the vast majority of purposes in organic chemistry, the stationary phase, what we're going to use here is either silica. So silica is an oxide of silicon with associated water molecules. Or another common one that's used is called alumina. Actually, I need just 1 minute. Hey, Lindsay, you want to...
Can we have the picture back? Oh, thank you.
Oh, can we stop this? Yeah. Thank you.
Okay, so these are the most common of the stationary phases. So if you're looking at these two, would you say that these are polar or non-polar substances?
I think they're polar because of water.
Yep, exactly. These are actually very polar. Now, central to this discussion is going to be something that you've known for quite some time at this point. You probably, since Gen Chem, have heard that adage, like dissolves like, right? I'm going to broaden that out for the purposes of this discussion, and we're going to say like interacts with like. Okay, that is really going to be at the heart of this discussion. So, these are by far the most common stationary phases. By the way, sometimes you'll hear these referred to as adsorbents, but they're certainly not the only ones. If and when you take biochemistry, if you go into a biochem lab, you're likely to see something that's called reversed phase chromatography. And for that, what they use are these little beads, and off of those beads, they have a bunch of different things. You can buy a bunch of different types, but usually some sort of an alkyl chain. And because the beads, the stationary phase, are coated with alkyl groups, it makes for a very nonpolar stationary phase. And so why would you use that? Well, think about biochemical molecules for a minute. Most biochemical molecules are fairly polar. So take like just a random monosaccharide. So this would be an example of a monosaccharide. So look at how polar that molecule is. I mean, you've got 5 hydroxyl groups on it. So remember, like interacts with like. So if you were to put a very polar molecule like this onto a very polar stationary phase, it's going to stick like glue. And you're going to be washing that column till Christmas time, and that thing's probably never coming off. Okay? So what they'll do, if they're working with very polar molecules like peptides or nucleic acids or sugars, they'll use a non-polar stationary phase. Because again, like interacts with like. This very polar molecule is not going to interact strongly with a non-polar stationary phase, and so it moves down the column a lot easier. All right? So when you take biochem, you'll probably experience that, but for our purposes, what we're going to be using is silica. Okay, so we can change the type of stationary phase we use. We can also change the mobile phase. So in column chromatography, the mobile phase is usually what we call a solvent system. When I say solvent system, it's usually a combination of 2 solvents. In a certain specified ratio. And typically what you see is it's usually a combination of a non-polar, or say relatively non-polar solvent with a relatively polar solvent. So for instance, in our chromatography, what we're going to be using is a mixture of hexane plus ethyl acetate. So if you're looking at those two, which one is the more polar component? Yeah, the ethyl acetate, right? It's certainly not going to be the hexane because that's just hydrocarbon. So we have a non-polar component of our solvent system combined with a polar or more polar component of the solvent system. And that's one of the things that you're going to do today is figure out what ratio of these is going to be good for our separation. All right? When you're trying to determine that, we do that by RF. So you're going to run a TLC plate, and I'll give you details on this in a minute. But you're going to run a TLC plate, and you're going to look at the RF of the spots. And ideally, for most applications in column chromatography, you want to use a solvent system that's going to give you RF values somewhere between 0.25 and 0.3. Said another way, you want to choose a solvent system that's going to give you the RF of your desired spot or spots somewhere between 1/4 and 1/3 of the plate. As you're going to find out as we go through this discussion with column chromatography, it's a lot of kind of Goldilocks scenarios. Meaning, with this, you don't want it coming down too fast, but you don't want it coming down too slow either. You want it coming down kind of right in the sweet spot, and that sweet spot is between 1/4 and 1/3 of the plate. Right? We don't want it coming down too fast because, yeah, that'll be a fast column, but your separation is not likely to be good. Right? I mean, if it's coming down in a shot, you're really giving those mixture components, you're not really giving them enough time to interact with the silica and thus separate out. So yeah, it'll be a fast column, but you're not going to get any separation. On the other hand, you don't want it coming down too slow either, because you don't want to be running your column till next week, right? You would like it to end at some point. So you kind of have to find a sweet spot between separation and the things actually moving down the column. Okay? Now, kind of the take-home message here with varying the mobile phase is the more polar the solvent, the faster everything travels. Okay? So as you increase solvent polarity, everything moves down the column faster. Okay? So, for instance, if I had 2 TLC plates, and I ran one of them in 10% ethyl acetate hexane, and you run the same plate in 50% ethyl acetate hexane. Your spots in the less polar system are going to be further down the plate. Maybe they would be like this. Whereas the spots in the more polar are going to be very far up the plate. Everything travels farther the more polar the solvent system. Okay, so that's TLC. Now we're going to be doing some TLC, but the primary purpose of this experiment is to do column chromatography. Well, column chromatography you can think of as just TLC turned upside down. All right, so think about that for a second. Let's compare these two. So with TLC, you grab the plate, you spot the mixture at the bottom, and then you allow the solvent to carry the mixture up the plate. Remember that? All right, well, the column is just that upside down. The column, you add the mixture up top, you allow the solvent to run down and carry the mixture down the column. So TLC, we spot at the bottom and let the things run up. In column chromatography, we put the mixture at the top and let everything run down. Okay, so they're just mirror opposites of one another. Now, we can tell a few things about the nature of the polarities here. Let's say I've got a two-component mixture. And I want to kind of correlate these two things with the things on the TLC plate. On the TLC plate, I'm just going to call these spots A and B. Which of those two is more polar? Spot A or spot B, given that behavior on the TLC plate?
That one should be more polar because it's going up faster.
Which one?
So, you're saying between A and B, right?
Yeah.
So A, because more polar is getting faster.
Doesn't the polar stick to the plate?
Yeah, exactly. So remember, like interacts with like. So in both cases, the column chromatography and the TLC plate, you're using silica as a stationary phase. So if like interacts with like, that means we know silica is a very polar stationary phase, so that means other very polar things are going to stick to it. And if it's stuck to the silica, it's not moving up the plate or down the column. It's just stuck. So by that logic, B is not moving up the plate nearly as well as A is. And so we would say that B must be more polar than A. Now let's compare that to the column now. Looking at my column, I'm chromatographing this mixture that I applied. It separates out into the blue band and into the red band. Which of the two bands is more polar?
Red.
It's going to be the red. Because again, our stationary phase is very polar. Like interacts with like. So very polar molecules are going to stick to the silica. And if it's stuck to the silica, it's not moving very fast. So the fact that the blue is moving faster than the red tells you that the red must be more polar.
This is going to be an interesting video that I'm Good thing for fast forward, right?
You should just upload this as a lecture.
What's that?
You should just upload it as a lecture.
Okay, so does anybody have questions about that? Because it's kind of fundamental with regards to column chromatography. It's kind of the basic principle of column chromatography.
So there's going to be a solvent in the column chromatography, right? That's going to be the polar
Yeah,
one?
so the solvent is what's carrying those things through the silica.
So what's the solvent in this case?
The solvent's going to be the solvent system, a combination of ethyl acetate and hexane, and it's going to be in some ratio that is yet to be determined.
Oh.
Okay. But
Does the
oh, yeah,
silica just look like sand?
yeah, it does. It's a
So we're just going
white
to be like pouring stuff into the sand and then watch it percolate through?
kind of. Well, except you're not going to be able to see it go through
Okay.
because, well, everything we work with in organic chemistry is either white or colorless, and so you never see any color. I mean, in theory, if you were working with a highly colored substance, you could watch it kind of go through the column, but we never work with highly colored things in organic chemistry, so we won't be able to see it. Are there any other questions about kind of the, yeah?
I was gonna clarify something. So when you have a more polar solvent, both parts of a mixture travel farther
Yes.
together.
Yes.
And then when you have the more polar part of the mixture, it's gonna travel less than the other part of the mixture.
Yeah, so and that's what I want to focus on right now actually, is why is this true? You know, I think it should probably make good sense to you that if you make the solvent more polar, the more polar component is going to come down faster. Right? Because again, like interacts with like. So if you increase the polarity of the solvent, then the more polar thing is going to spend more of its time in the more polar solvent. And if it's spending time in the solvent, it's moving. That's the mobile phase. So the more time it spends in the solvent, the faster it comes down. So the more polar the solvent becomes, the more time your polar component is going to spend in the solvent, and thus moving. What confuses what confuses some people a little bit is that everything moves down faster in the more polar solvent. So why would it be that even if you have a less polar component, that increasing solvent polarity causes it to come down faster too? So the way I like to picture this is I like to picture the column, the silica, having a bunch of binding sites on it. And normally we think of the mixture components interacting with those binding sites, getting stuck on those binding sites on the silica. But solvent does too. So as you increase the solvent polarity, you have more of the ethyl acetate in our case, then the more solvent is going to be stuck to the silica binding sites. And I kind of like the analogy of it's almost like a parking lot. You know, if you pull in a parking lot, you cannot simultaneously pull into a parking spot that's occupied by somebody else. You've got to keep on moving down the line until you find an open spot. It's kind of the same thing here. If you have a bunch of solvent stuck to the silicon binding sites, the molecules of the mixture cannot simultaneously occupy them. So they got to keep on flowing down the column until they find an open binding site. So the more solvent you have occupying those binding sites, the less are available for the solvent mixture, and so they just keep flowing down. Okay? But the bottom line is this. The more polar the solvent becomes, the faster everything travels. Okay? Okay, so let's go into the third thing that we can change. The third thing we can change is the size of the column. Said another way, the amount of silica used. The more silica you use, the bigger the column's going to become. And this is a very general rule of thumb. If you use X amount of mixture, we want to use 40X amount of silica. So simply put, if you're separating a gram of material, you want to use a column made up of 40 grams of silica. Okay, 40 times the amount of silica relative to the amount of mixture. But again, very general rule of thumb. So if you have two different separations you're trying to perform, let's say we run one TLC plate to look at the separation, and it looks like this. And then you're running a different separation, and it looks like that on TLC. One of those is going to be a very easy separation, and the other one's going to be a much harder separation. If I call these A and B, which of those is going to be an easier separation to accomplish? Yeah, A. Because they're separated by a mile. They're not running anywhere close to each other. So in a case like that, where you have really good separation, where they're running very differently from each other, you might choose to use a smaller amount of silica. Just a tiny little plug would probably work for that. However, if you're talking about something like B, well, those are running very close to one another. That's going to be a much more difficult separation. at which point you might want to use a little bit more silica, make a bigger column, just to give them more time to separate out from one another. Okay. Does anybody have questions about that?
I was just gonna ask
Mhm.
real quick, so whenever we do column chromatography, we're always generally doing TLC alongside of it.
Mm-hmm. Yeah, they're always done in tandem.
Gotcha.
And we'll get into that in just a second.
Gotcha.
Okay, so then the fourth and final thing that you can modify is the rate of flow. So the faster the flow rate, the higher the flow rate, the faster things come off the column. This is kind of a moot point for us because we're not going to be pressurizing our column. We're going to do what's called a gravity column, meaning we're just going to open up the valve and the solvent's going to drain through by the force of gravity. People don't usually run columns that way, however. Normally people pressurize the column. So you'll notice that in every fume hood, you always have these air lines, right? And the point of them, well, there's several uses for them, but one of the more common ones is you attach tubing like this, and you can get a little glass adapter that fits in, and you can clamp it to the top of your column, and then you turn on the air, and that pressurizes the column, causes it to flow faster. And you can obviously adjust to that. You know, if you want it to run slower, you don't pressurize it as much. If you want it to run faster, you crank up the air. But that's another thing you can vary when it comes to running these things, the degree of pressure that the column is run under. Okay? Any questions on any of this kind of background stuff? So what I'm going to do now is I'm going to give you the actual procedural details, the kind of the nuts and bolts of what you're going to come in and do on Wednesday. So there's a few things that you've got to do in order to set up before you can even add your mixture to the column. And the first thing you're going to have to do is you're going to have to pack the column. So there's a couple of different schools of thought to packing a column. There's what's called the dry pack method, and then there's called the slurry method. And for reasons I'm not entirely clear on, for some reason, the Europeans tend to prefer the dry pack method. I always learned the slurry method because I'm not European. And, you know, different people will claim one is better than the other. The Europeans swear by their dry pack method. It's never worked for me. So I'm going to teach you the slurry method. Because that's what all I've ever used. If you go and you work for somebody from Europe or work with somebody from Europe, like in a lab at a university, they might try to tell you to use the dry pack method. But anyway, this is America, so I'm going to show you the American way, which is the slurry method. With the slurry method, the first thing you're going to do is make your slurry. So what is that? Well, you're going to get a beaker, and you're going to add, I don't know, I'd say approximately 40 mils of the solvent system to the beaker. And then from there, add your silica to the solvent with stirring. Now, by the way, this should all be done in the hood. The silica is very, very fine and if you're just working with it dry out on the bench or anything like that, it creates dust, and it's quite hazardous to breathe. So you want, anytime you're working with the dry silica, you want it in the hood. Okay. But this combination, it's a suspension of silica and solvent, is your slurry. And rather than getting too caught up in exactly 40 mils, and I told you 40 times the amount of mixture to the silica, I gave you that number. Instead of getting too caught up with those values, you're looking more for a consistency. Okay? Again, it's kind of a Goldilocks thing. You don't want it too thin, but you don't want it too thick. And so what I usually equate it to is like, those drinks you go and get at the gas station, like the slushy, icy type drinks. That's about the consistency you want. You want it thick, but you still want to be able to pour it. Okay, so it can't be too thick, right? Otherwise, it's not going to pour. So it should be thick, but still pourable, I would say. All right. Once you've got the slurry made, set it aside, and then you're going to add, I would say, about an inch of solvent system to the column. So you grab a column, put about an inch of solvent in, and then pour the well-stirred slurry into the column. So before you pour the slurry, just make sure you get it stirred up really well, because it will separate, right? The silica is a lot more dense than the solvent, and so if you let it sit for too long, it's going to separate out. And if you go to pour that separated slurry, you're going to end up decanting it. You'll pour all the solvent, and all the silica will remain in the beaker. So get it really well mixed, and then pour it in. All right. So once you do that, you'll fill it up. What you'll notice is, as that slurry kind of pours down the walls of the beaker, as the solvent evaporates, you're going to be left with a bunch of kind of sandy residue. All right, you want to rinse that down. So after you pour the slurry into the column, rinse the walls with the solvent system. And that's just going to get all of that sandy residue down. All right, and then what you're going to see is, after a minute or two, the silica in the column will actually kind of separate out. So what you'll see is something like this. You've got all the silica kind of sunk to the bottom and the solvent kind of on top of it. What you're going to do after that is you're going to open up the valve and drain the column. But not too much, okay? Because this is one of the cardinal sins of column chromatography. Never let it run dry. Okay, so you're just going to try to drain the solvent down until the surface of the silica is just barely exposed. Don't let all the solvent run out, otherwise you're going to incorporate a whole bunch of air into the silica, and it's never going to separate anything. Okay, so you're just going to drain it down until the solvent is just barely exposing the surface of the silica. All right. So once you have that, you're ready to prepare the sample, the mixture. So for the mixture, I believe the lab manual is telling you to do about 200 milligrams of the mixture. So you're going to weigh that. Into a small beaker. And here's the most critical part. You're going to dissolve the mixture in a minimal amount of ethyl acetate. Okay, so there's two things to notice here. Minimal amount. This is the most common reason why columns fail, is people dissolve their mixture in too much solvent. So when I say a minimal amount, you're probably looking at, I would say, half a pipette full at most. Okay. The other thing to pay attention here is, notice we are not using the solvent system. We are using pure ethyl acetate. All right. So the point here, what we're trying to do is we're trying to make a very, very concentrated solution of the mixture. Okay, it should be so concentrated that it's actually thick, that it's viscous because it's so concentrated. All right. So you're going to have your small beaker. You'll have the 200 milligrams or whatever, and then you're going to add slowly a very small amount of the ethyl acetate, and it's going to make that highly, highly concentrated solution of the mixture. Once you're ready, you're simply going to take a Pasteur pipette. You're going to pipette the mixture down the walls of the column. Right? So you're going to have your Pasteur pipette. Looks a little bit like a turkey baster, but that's okay. And then you're just going to pipette it down the walls. And the point of this is that, you know, if you were to take your pipette and just kind of squirt it on the column, that's going to really etch and chew up that surface of the silica. By slowly dripping it down the walls, it allows the mixture to be added to the surface of the silica in a nice uniform layer without disturbing the top layer of silica. All right, so pipette it down the walls, and that way you will keep a nice uniform surface of the silica. Once you've done that, you're going to drain it into the silica. So once you've pipetted it all on the top of the silica, you're going to open up the valve and allow it to drain into the silica. But remember, don't let it run totally dry. Just allow it to run into the silica. Then what you'll do is, with about a half, because after you put that pipette, that really concentrated liquid down the wall of the column, you're going to have this sticky residue. And so what you'll do next is, with about a half a pipette full of ethyl acetate, wash or rinse the walls of the column. So just get a half a pipette or so of ethyl acetate and just kind of rinse the wall of the column just to get that residue down. Once you've done that, you'll drain that into the column. Okay? last step here is you are going to add about 1 inch of sand to the top of the silica. When I say sand, I literally mean just like from the beach. So put about 1 inch or so of sand on top. And the purpose of the sand is to protect that silica layer. Remember, you're going to be continually dumping solvent system in. You know, as the column is running, you're going to be using up that solvent system. So you're going to need to continually fill it up. Well, if you didn't have anything protecting that silica layer, as you just dumped solvent in, that would wash up that top silica layer. Okay? So by putting a little bit of sand on top, that's just going to protect that top silica layer as you pour in the solvent. Okay, so add the sand, and then you can fill up the column with the solvent. And then let her rip. Open up the valve and start the column. And at that point, you would start collecting your fractions. All right? Does anybody have questions about the procedure up to this point?
So when you say drain into the silica, do you just mean open up the valve? Or?
Yeah, just open the valve, and that'll allow the mixture solution that you just pipetted onto the column, it'll allow it to drain into the silica.
So we will be losing some of that, the slushy material, right? Because you're going to open up the valve and let it flow.
Well, the slurry is what contained the silica. So that is going to be already kind of packed in there.
So it's not going to be coming out the...
No. The silica is not going to come out as you run the column.
Okay.
The silica is stuck in there. The only thing that's going to be coming out of the column is the solvent. Mm-hmm.
So, since everything's clear, how do you know how long to leave it open?
Well, I'm glad you asked that. Because that's what we're going to talk about now.
Okay.
That's a very good point. How you're going to sit there for probably a good 30 minutes to an hour collecting test tubes, end up with probably 50 of them in the end. How are you going to know where your compound A, where your compound B of the mixture is? Well, for that, you're going to need to use thin layer chromatography. Okay? So, actually, before we get there, I just want to give you a couple pointers here. So, number one, we want the bands coming down the column perfectly uniform. Okay, we don't want them angled, we don't want them bleeding into one another. We want the bands completely uniform as they travel down the column. So, a couple of things to keep in mind to help ensure uniform bands is number one, make sure your column is perfectly straight. Okay, you don't want the column angled. It shouldn't be like the Leaning Tower of Pisa. It should be perfectly straight up and down. Because otherwise, if it's angled, that's how your bands are going to come down the column. They're going to be angled. They're going to be non-uniform. The second thing, no air bubbles. This is one of the reasons why we never let the column run dry, because that incorporates air bubbles. If you have an air bubble, what ends up happening, you've got silica, and if you have a giant air bubble in it, what happens is the band will start making its way down the column, ahead of the air bubble. But then once it passes through, it results in a leading edge. Meaning you get something kind of a jagged, almost tooth-like structure, where the stuff that went through the air bubble is way ahead of the rest of the band. And that tooth-like structure can actually bleed into other bands, causing mixed fractions. Okay? So just a couple things to be aware of. So, okay, let's go ahead and talk now about how we're going to monitor the column. Danielle's question. So you're going to use TLC to monitor the column. Now, you all did TLC last semester. You probably did those cute little test strips. We're not using those kind of TLC plates. We're going to use some really fat ones. And also, I wouldn't worry about testing every single fraction. You know, you don't have to TLC every single test tube. I would probably do every other. So you're going to start collecting your fractions, and maybe you'll just TLC fractions 2, 4, 6, 8, 10, 12, 14, 16, for instance. Just do every other one. And hopefully what you'll see once you run the plate, hopefully, initially you're going to see nothing, right? Because the mixture is way up at the top and it's got to make its way down the column. So the first few fractions, you're going to have nothing in them. But then, hopefully you'll see something like that. As that first less polar thing comes off, and then you'll see nothing, because there'll be a little separation between the two things. And then something like that. As that second spot, the more polar thing comes off. And so what you would do in a case like this is you would grab 2 beakers, one for each spot, and then you would combine, let's see, it looks like I've got the first, my fraction A, I'll call it, is coming off in fractions 6 through 10. So I would grab test tubes 6 through 10, combine them into a beaker. And then it looks like your second spot, spot B I'll call it, is coming off in test tubes 14 through, well, down the way of it, we'll just say 20. So then you'll take test tubes 14 through 20, dump them into the second beaker. And so in the end, all you have to do is then evaporate the solvent from both beakers, and you'll be left with pure component A in one and pure component B in the other. Does that make sense? Does anybody have questions on that?
So when we weigh the mixture into the beaker, you said it needs to be 200 grams, or?
Oh, the 200 grams is for the mixture. So you're gonna start this whole thing. Here's the mixture. So you just weigh out 22 grams of this, and that's what you'll ultimately dissolve in the minimum volume of ethyl acetate. And that's what you'll put on the column. But in the end, you've got all those fractions, all those test tubes. The TLC will tell you which test tubes contain your product. And so based off of that, that's going to dictate which test tubes you combine to get the pure A and the pure B. Okay. Any other questions on that? Okay, so that's a perfect world. Sometimes what you'll see is you might see something like this. So what we're looking at in this case is you have a few mixed fractions here. You see how, like, I guess I would call that spots 9 through 11, maybe? How both spots are in those fractions? That's not good. I mean, it's not the worst thing in the world. It happens to the best of us, but it's not really what you want. So in a case where you have mixed fractions, meaning you've got both spots in the same tube, don't collect those. Throw them away. Right, the whole point of this entire exercise was to get A away from B. So if you add your mixed fractions together, then you're just contaminating your pure A and pure B. So if you should see that you have mixed fractions, throw them away. Any questions on this? Okay, so let's talk about what you're going to do today. That pretty much will get you through, I think, everything that we're going to do next Wednesday. What you need to do today to prep for next Wednesday is the 3 things. You need to pull spotters, and you should probably get about 3 of them. So you technically only need 1, but they're pretty delicate. So in case one breaks, you want to have at least 1 or 2 in reserve. You need to wash test tubes, and I would recommend you label them as well. All right, so the test tubes are right here. These little plastic tubes. I would put them in a rack. So use these little white test tube racks. By the way, whenever you pull the spotters, the double open-ended capillaries are right here. Whenever you want to do that. Wash and label the tubes. So remember, you're going to need about 50 of these. And so if you collect 50 test tubes in a rack, and they're not labeled, it's very easy to get disoriented, right? So you want to make sure that you know which tube is which, because on the TLC plate, you're just going to have numbers. You want to be able to easily correlate the numbers on the TLC plate with the number of the test tube. Okay? So that's why I would strongly recommend not only do you wash these, but label them as well. Okay? That's 2 things. The third thing you're going to need to do, and I would recommend we do this as a group, is determine the solvent system. Okay. Now, I don't think I'm not sure that I mentioned this yet or not, but you're going to work in pairs on this because it's kind of a lot to keep track of the first time you do it. There's a lot of moving parts, and it's a lot easier to manage with 2 people working on a column than just everybody doing his or her own. So I don't really care how you decide to pair up. There's an even number of us, so we should be able to split into 6 pairs. But the way I would suggest doing this is one lucky contestant gets to babysit the column, meaning you sit there and switch out test tubes, one after the other, after the other, after the other, and also keep your eye on the solvent. You never want to let the solvent run dry. So as the column is running, obviously you're going to have to continually refill and just make sure that the column keeps running. The other lucky contestant gets to handle all the TLC work. So they'll be taking the fractions, spotting them on the plate, running the plate, developing it, marking the spots, calculating RFs, etc. Okay? So that's going to be the division of labor here. And again, I don't really care how you decide to divide that, but one of you can do one thing, the other one can do the other. If you feel like it, you can switch out halfway between, whatever you want to do. But as far as the person doing TLC stuff, a couple of things about that just to refresh your memory. So you never want to handle the TLC plates with your fingers. Remember, your oils will kind of contaminate the silica. So you always want to handle it with the forceps. When you go to pull a plate, you always want to have two things in hand. You want to have the forceps in one hand and a pencil in the other. Because as soon as you pull the plate out of the developing chamber, you need to immediately mark the solvent. Remember, the solvents are fairly volatile. So if you pulled the plate and decide, oh, all right, I'm going to take this back to my bench, and then put it down, grab your pencil, there's going to be no more solvent from it because it will have long evaporated. Right, so as you go to the developing chamber to pull out the plate, make sure you have a pencil in hand so you can pull the plate, mark the solvent front, all within a matter of seconds. All right. The third thing, when you calculate the RF, remember, when you're calculating the RF values, this is a simple ratio. The RF, you're going to measure the distance the spot moved. So, for instance, and you're always measuring from where you spotted, not the bottom of the plate. So the distance the spot moved divided by the distance of the solvent. Okay, so that would be from there. So it's a simple ratio. The two other things of note: you never let the solvent reach the top of the plate. So you want to pull the plate before the solvent reaches the top. And then finally, remember when you're spotting. When you're spotting, you want a small concentrated spot. Okay? So you probably want to just kind of hit it with the spotter 3 or 4 times pretty quickly. So dot, 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 dot. You don't want to just hold the spotter on the plate and let it drain completely out, because then you're going to get this fat, diffuse spot that's going to not run very well. All right. Okay, any questions on this? All right, so like I said, you and your partner have 3 things to do today. You need to pull spotters, you need to wash and label tubes, and you need to, what will all together kind of figure out the solvent system. So what I would recommend we do for that is I'm going to put 6 concentrations up on the board, and I would recommend we get started with that first because it takes a little bit of time for TLC plates to run. So why don't you start with the TLC, and then while those plates are running, you can work on the pulling of the spotters and the labeling of the tubes, etc. Okay, but we'll just put a table up here. We'll do let's do concentration. We'll do whoever decides to do it, whatever pair, and then we'll put RF over here. 1, 2, 3, 4, 5, and 6. All right. So let's do 100% ethyl acetate. We're going to do 50-50. Remember, this is ethyl acetate combined with hexane. right? Okay, so let's do that. So what I would like for you to do, you and your partner come up and sign up for one of these concentrations. You'll need to make a little developing chamber, which are in the back underneath the third fume hood. There's a bin of a bunch of those little jars. So grab one of those. What I would recommend, just for the ease of making your solution, is just get your 10 mil graduated cylinder and make up 10 mils of solvent. Okay, that's going to be the easiest way handling the percentages, I think. So you'll make up whatever concentration that you sign up for, and forceps and the plates set out here. So here are the TLC plates, these are the forceps. You'll go ahead and spot the plate with your mixture, which I set out over there. Then run the plate. When it's ready to be pulled, pull the plate, calculate the RF, and you can put in your data here. We'll kind of collect all of this, and then when we're done, we'll have a look, see which solvent system looks best, and then and that's what we'll use.
Wait, what are we spotting with?
The mixture. So you're going to need to make up a TLC sample. So what I would do is just grab one of your small vials that you have in your locker, and using a spatula, just take a tiny amount of the mixture, just like the tip of a spatula amount, and put it into the vial, and then dilute it. And it really doesn't matter what you dilute it with. Probably ethyl acetate would work, so we're going to have that in the fume hood. Acetone would work. It really doesn't matter, but that's what you're going to end up spotting. So you'll add a few mils or whatever of the solvent, and then you can use using the spotter. You put it in the TLC sample, it'll be drawn up through capillary action into the spotter, and then that's what you'll spot on the TLC plate.
So we do need to make the spotter first.
Yeah, I guess you do.
Okay.
But like I said, try to get this going as soon as you can, because again, it's going to take a while for everybody's TLC plate to run. While the TLC plate is running,